From SVC College of Engineering, and today we're going to learn about a very interesting topic, which is the working of MOS transistor in different modes. So, moving on to our next slide. So, before jumping into the topic, let me explain the basics of this topic. So, MOS transistors are of two types, which is NMOS and PMOS. NMOS transistor consists of a trivalent substrate, and PMOS transistor consists of a pentavalent substrate. So the transistor, so as you can see on the screen, here's the diagram of the transistor. So there are basically three components, which is source, gate, and the drain. So in N-type NMOS transistor, both the source and drain are made up of trivalent substrate, and the P-type substrate is the below bottom line is made up of P-type substrate. So moving on to our next slide. So moving on to our next slide, we are going to explain here about the flat band diagram. So the term flat band refers to the fact that energy band diagram of the semiconductor is totally flat, which implies that no charge exists in the semiconductor. The flat band diagram of an aluminium silicon dioxide silicon MOS structure is shown in the figure. The flat band voltage is obtained when the applied gate voltage equals the work function difference between the gate metal and the semiconductor. If there is a fixed charge at the silicon interface, the expression for the flat band voltage must be modified accurately. So as you can see in the diagram, uh, as you can read the graph here, it's as we go up, it's E, and EV refers to electron volts. So moving on to our next slide. So accumulation mode. In this mode, there is accumulation of holes at the silicon oxide interface. All the field lines emanating from the gate terminal on this layer giving an effective dielectric thickness as the oxide thickness. In this mode, Vg is less than 0. Ec is equal to conduction band energy level. Ef is equal to Fermi energy level. Ev is equal to valence band energy level. Ei is equal to intrinsic energy level. Q is equal to charge of electron. Vg is equal to voltage applied on gate. Then psi s is equal to surface voltage. Q is equal to charge of electron. Accumulation occurs when one applies a voltage which is less than the flat band voltage. The negative charges, which are also known as holes, from substrate to the oxide semiconductor interface. Only a small of band bending is needed to charge, so that almost all the potential variation is within the oxide. So moving on to our next slide. So the second mode we are going to discuss about is depletion mode. As we move from negative to positive gate voltages, the holes at the interface are repelled and pushed back into the bulk, leaving a depleted layer. This layer counters the positive charge on the gate and keeps increasing till the gate voltage is below threshold voltage. In depletion region, voltage applied to gate is greater than the flat band voltage and less than the threshold voltage. As a more positive voltage, then the flat band voltage is applied. A negative charge builds up in the semiconductor, and the charge due to the depletion of semiconductor starting from the oxide semiconductor is the depletion layer, which further increases with increasing gate voltage. Moving on to our next slide. The third and the final mode we're going to discuss about is the inversion mode. When Vg crosses threshold voltage, the increase in depletion region which stops, and charge on layer is countered by mobile electrons at silicon oxide interface. This is called inversion because the mobile charges are opposite to the type of charges found in substrate. In this case, inversion layer is formed by the electrons. Field lines hence terminate on this layer, thereby reducing the effective dielectric thickness. As the potential across semiconductor increases beyond twice the bulk potential, another type of positive charge emerges at the oxide semiconductor interface. This charge is due to minority carriers, which form an interoxide layer. As one further increases the gate voltage, the depletion layer width barely increases, which in turn causes the charge in inversion layer increases exponentially with the surface potential. So, moving on to the next slide. Thank you so much for watching this video, guys. Hope you enjoyed the video. Bye bye. Take care. Merry Christmas.